if we can get this rock physics data, and I'm showing you there's a variety of sources and some methods, what do we do with it? Here's a typical workflow where we take, say, the well logs and we make all the corrections that we need to. We do metaphysical modeling, so we have a combination analysis of the Holy Trinity, VP, VS, and rho, plus maybe measurements of anisotropy, porosity, fluid content, and aspects like V shale, etc. So we've got almost the four things that we want to know about, but at the well logs. We can use that to do 1D modeling, so in the 1D sense we know what we're looking for. We can use these predictive 1D models to help us with our attribute contributions. We can look at multi-node trend analysis, so we can see the variation, rock properties over depth or over heterogeneity. And we can forward model these scenarios. I think once we get to the forward model, we've got a lot of potential. The forward model then starts to educate us. In fact, the whole process is a process of educating the geophysicists and the geologists together. We're taking something out of one domain and putting it into another. If you understand the process and you understand the modeling algorithms that we use, you can start to look for the aspects, the interpretation aspects that you need to see in your data to make sense of it. So to the forward modeling, it's kind of inversion in the brain is the way that I always think of it. In that you know pretty much what you're putting in and you see what comes out. The problem with inversion is that, as we know, that there's an element of ambiguity in interpreting the inversion. Forward modeling, you've got a system where you know what's going on. Then we're really sort of depending on understanding whether our seismic data can deliver what we want it to deliver. And that means that we need to understand it, we need to understand the way the wavelet arrives. As has been said before, the logical place to start on this, obviously, is the well tie, the wavelet extraction. If you have VSPs, full 3-component or 3D VSPs, so much the better. I think the time is right, because I think the gentleman at the back was saying for a renaissance in the use of some of these tools. We have backlogs of VSPs going back maybe 20 odd years. There's useful information in them, particularly in making these kind of calibration steps. So we can then look to see whether it is worth looking towards an inversion. Some good things about inversion, as I mentioned earlier. It's really down to understanding whether you're going to get out of the inversion what you need to see. So again, you're using all these steps to condition whether you understand enough to go ahead to the next step. Many kinds of inversions. I'm not going to dwell on too many of them here. I think a number have been mentioned: colour, deterministic. I mentioned stochastic, downscaling capabilities. We've got so many ways of delivering this kind of thing. But the key thing is, if you invert without knowing what the rock properties innate in your understanding are, you're going to get to a point where you really don't understand what you're looking at. And that's where I think many of our mistakes in our 50% success rate max swings comes from. It's not really understanding why the well was drilled, why did we get the result we didn't bargain for. So I'm now having sort of, if you like, set the scene. Where do the rock properties come from? What kind of workflow do we go through? I'll take you a few examples, starting with some very simple ones, right the way through to time-lapse and stochastic inversion. This is a rather nice one where this is a chalk reservoir that's been inverted to porosity, and we've got a very simple linear relationship, or almost linear relationship between acoustic impedance and porosity. And so it's very straightforward to go from this full stack silent data to a porosity inversion calibrated at a well. So you've got a well tie, everything's working for you. That's good science, and it's a good, straightforward, simple example. Here's an example where value was added. You can see there's a well just off the section, which found a water-wet sand. Very good well tie to the water-wet sand. This was the previous interpretation over the top of the structure. A rock physics model was derived from that water-wet sand, such that we could just understand, if you like, the polarity. Again, very simple rock physics, but good rock physics, in that we can understand the polarity of the loops that we're looking at. No inversion here implied. This is straight reflective slightly. Some very obvious things. You can see the blue represents a water-wet sand, where you're going from positive to just about a negative loop over here in water-wet with the relationship with sine squared theta. If you fluid substitute into that reservoir, you should expect the whole thing to move down and become slightly more negative, softer if you like. So you move from a slight positive to a strong negative here. And this represents a shale over oil sand loop. So you're looking to move from this to this. When you apply that to the interpretation of that image, you see that if that was true, then, and this was oil filled, you should take the interpretation up and over. But actually what you've been picking as the top reservoir, in fact, represents a loop over the top of the oil-water contact. And it's like everything, once you know what you're looking at, you start to recognize other aspects of the model. You can start to see the reflected terminations, terminate out the contact, etc. This is a very good example of rock physics being used in a farming where the original reserves put into the structure were something like 50 million, in fact turned into 300 million barrels. This is a Norwegian example on farming, so some happy examples. Another example, which a number of you, I think, probably will have seen, this is the oil render example, where nearby discovery, 4 or 5 million barrels, just enough information, if you like, to do a rock physics model, which is very similar to the last one you see. You see the water-wet space and sine squared theta going from the near stack to the far stack. You went from positive to slight negative. You put oil in that. You're predicting it would go from a medium positive loop to a medium negative loop. You stack the whole gather there, and you're going to get, if you've got oil, you're going to get a very dim on the top here. So instantly said that we should look for something very conversant and far offsets with oil. Means it's going to be very difficult to pick the top reservoir and the polarity of data we're looking at. Here's an example. This was done with GX technology now ion. And you can see that when you start to know that you have to look for regional analogues, which is one aspect of what would be the analog, but also starting to look for the right kind of data, you start to see some very interesting things where producing fields light up. So does the exploration or quasi-exploration target of render. Again, a very nice, simple example of using rock physics, but enabled the operator there to go on and do some very much more sophisticated work from the discovery point into the reservoir of geophysics. And this is a good example where we're actually starting to see some real detail in the reservoir where the sand bodies and the inversion between the sand bodies is starting to make some real sense and be used to plan production wells with some good results. Here, for example, is a case constrained where I'll show you where the production well went. With this one, we'll start to pick up oil saturation, 15, 17 meters here. You start to see a few meter scale barriers underneath the oil-producing sand. So when you've got situations like that, these are good places to put producers because if you've got a shale underneath, you're not going to get water ingress coming in very quickly. So this kind of definition of the meter scale is extremely useful.